Okay, so volume of a solid of rotation. Does everybody have this copied down already? Yeah? Okay. So the idea behind a volume of a solid of rotation, or in this case they call it a revolution, um, is that we're going to take an area, and in order to find a volume, we're just going to move that area around. We're going to rotate it around some axis. And so this example right here will kind of let you visualize it, because being able to visualize these problems is actually the most difficult part of being able to do this. Usually if you can visualize it, then you can come up with a pretty good integral to actually be able to calculate it. Okay, so you can see what I have right here is, let me just move this back to its original position, right, is the area between two curves. Okay, and whenever we're dealing with a volume of a solid of revolution, what we're going to take is we're going to take some area, and in this case, we're actually going to rotate it around the x-axis. And so what I'm going to do is we're just going to take that area, and if you could imagine that it was just kind of on a hinge, and it's just going to swing all the way around the x-axis, okay? Now, when it does that, it's going to create a solid. Okay, so you can see the way this thing is going to look. It's going to create a volume of this whatever kind of solid, thing we would make, rotating it around. And this one looks kind of almost like a glass, but it's not very empty. Okay, and we can take this and you can look at it and see that there's just going to be a hole kind of straight through the middle. But the idea is simply that we're just going to take that area, whatever the area is, and we're going to rotate it around an axis, and we're going to get some kind of volume that's going to be created there. And so we're actually going to use an integral in order to calculate the exact volume of this solid. And we can do it with pretty much any shape that we want. Okay, so here's an example here. So go ahead and copy this example down, and we'll work with it. Okay, so we're going to find the volume of the solid obtained by rotating the function y equals x squared from 0 to 2 around the x-axis. So we're going to be using the function y equals x squared. Everybody knows what the x squared function looks like, right? It's going to be y equals x squared. And then we're going from 0 to 2. So from 0 to 2. I'll just put my 2 there. And so we're going to take, this piece right here. And let me do this so I can. We're just going to take the part from 0 to 2, and we're going to swing it around the x-axis, right? And so when I do that, I'm going to get a shape that's going to look something, if you could imagine with me the way this shape is going to look. It's going to, and my drawing is not going to be nearly as good as the Wolfram demonstration, but if you could imagine what this thing would look like whenever we rotate it around the x-axis, it's going to kind of look like a trumpet almost, but it'll be completely filled in, or like a Hershey's Kiss or something like that, right? So we're just taking that thing right there from 0 to 2, and we're going to rotate it around the x-axis, and we're going to create some kind of shape that's going to look like a Hershey's Kiss, right? And so there are a couple of different ways for you to find volumes of solids, and this is actually the most simple. And so we're going to be using what's known as the disk method in order to find this one, okay? So here's the idea. Is you can see I already have this disk drawn over here on the right-hand side of the screen. And if you just imagine that being like a quarter, so you're looking at a quarter basically that's facing you. And so it just makes a simple little disk. Well, just like with the area between from a curve to the x-axis. If you remember doing, when we did Riemann sums, so if we had this thing right here, what we would do is we would just use a bunch of rectangles, right? So we could use some right-hand rectangles, okay, to create a Riemann sum. And so we just used a whole bunch of rectangles in order to, find the area under a curve, right? And then we talked about how an integral, is an infinite number of Riemann sums. And so you're just taking all of the different little rectangles for every single height all the way in between there and adding them all together. Well, what we're going to be doing here now, a rectangle is a very nice thing that you could use in order to find the area of something, right? The area of a rectangle is a very simple formula. Well, now what we're going to be doing with this volume right here, we can't just use a rectangle anymore because we have a volume. Well, if you take a rectangle, any rectangle, and you swing it around the x-axis, what it actually creates is a cylinder, something like a quarter, right? And so we're going to use that exact same idea in order to create this. And so what I have here is just another Wolfram demonstration, but you can see that this is a disk method, and what we have are just a bunch of disks that are going to be used. Okay, so I'm going to use these disks in order to kind of show what we're doing. Let me see if I can get this thing to maximize, and let me get rid of the curve. It's more confusing than anything. All right, and so what you can see is that this thing right here, I'm going to cut it into just a bunch of pieces, right? And so the idea is, if we just had one, if there was an axis through the middle of this thing, going straight through the middle there, and what we did is we just take, one little rectangle, and swing it around, then you'll get a disc. And then so you can see we just do that over and over and over again. We take a bunch of rectangles and swing them around, and so we just have a bunch of discs that we need to add together. And so that's the idea behind the disc method, is that we're just taking all of these discs and we're going to add them together. So when you look at them, the important thing that you need to know, because you're trying to find the volume, so if you want to think about it as just finding the volume of one disc, right? You just want to find the volume of one of them, and then you just need an infinite number. But just thinking about it as the volume of a disc or a cylinder. A cylinder we're used to seeing standing up and down, but this one's kind of laying sideways. So this right here, the distance from, the center of this thing to the outside is going to be my radius, right? And if I took the quarter and I laid it down kind of flat like it was on a table, right, then what would you call this right here? What would that be? Yeah, it's your height. Okay, so this is your height. And now, in order to find the volume of a cylinder, remember what the formula for the volume of a cylinder is? Yeah, it's the area of whatever shape you have times the height. Okay, so you can see, let me pull this one up and we'll look at it for a second. So in this one right here, you can see it talks about, we need the area. And so the area of this, you see how they have one disc right in the middle of this thing? And so we're talking about that one disc in the middle. And so we need the area of that disc. Well, in order to get the area, we need the radius, right? Okay, and so what we need is area times height. But in order to find area, we need to use pi r squared times h, right? Because pi r squared is the area of a circle since we're using a disc right here. So we have pi r squared times h is the volume of just one disc, right? Okay, so now, this is the general formula for the volume of a disc, but now what I want to come up with is the formula for a disc in the problem that we're actually talking about, okay? So, if you would just imagine that, I guess this one right here, we'll just look at this one kind of in the middle here, okay? Just imagine there being one disc right here, and there's the front of it. So I know my drawings aren't the best, but just imagine there being one disc right there in the middle of this one that we're actually talking about. And so if you could imagine it like these. Okay, so I'm just taking one of these out, and we want to figure out how to find the area of just one of those from the problem that we have. Well, if you do that, then we need to come up with a radius. Well, for us, the radius is from the x-axis, to the curve, however far it is. That's going to be equivalent to our radius. So in our problem right now, the radius is just the function, right? So the radius is x squared. The radius is x squared. Now, the height, the distance across the face of this thing right here, is it's a change in our x value is actually what the height is going to be equal to, right? Because if however wide this disk is just a change in our x value. For example, this one looks like it could be going from, I don't know, that could be 1.7 and this could be 1.8. So the change in our x value right here would be 0.1, right? So the height of the disk could be 0.1 in this case. But the important thing is just that the height is equal to however far we've moved across, right? However wide our x value is. So height is going to be equal to our change in x value. And now if we start to use this volume formula right here, okay, we want pi times our radius, which is x squared, right? So the radius squared, so x squared, times height. Well, height is just our change in x. And then this is where the integral comes in, right? So this is already the formula for the volume. But remember, we want to use an infinite number of disks. But for every single disk that we make, if I made another one out here kind of on the very outside, if I made if I turned this into yet another disk, right? Well, the one thing that would stay constant is that the radius on this disk right here as well is still just the function, right? So the function is always the radius of every single one of these things that we're going to use. It just ends up, however high this thing is off of the x-axis, that's how much is going to get rotated around. And so what that means is that this radius right here is is the function right there is always the radius, and then pi times, here's the radius squared times the height. But the thing that we need to use an integral for now is to use every single height all the way from 0 to 2, right? So that's our whole purpose here, is that we want to, we're using all of these heights, and what I'm going to say is all of these heights are going to be every single one all the way from 0 to 2. And so you can see that this is just a simple, adaptation to the volume formula for a cylinder. We're just using the volume of multiple cylinders, an infinite number, in fact, to calculate this. Now, because of my properties of integrals, you'll see these set up most of the time where this pi right here can be pulled out front because it's just a constant. So pi times the integral from 0 to 2 of x squared. What's x squared going to be? Yeah, x to the 4th dx. Okay, now I'm just going to go to my calculator. And go on, and I'm just going to put this in exactly the way it looks. I'm going to go math 9. Okay, and I'm going to go, well, let me get my pi in here first. So let me go second pi times, and then math. I'm scrolling down to number 9 for the integral, and I want to go from 0 to 2 of, and I want x raised to the 4th power with respect to x, and this should give me a decimal number here. So this is saying that the volume of that shape right there would be 20.1, and I'm just going to round it to 06, so 20.106, and this would just be units cubed, whatever unit we had, since it's a volume, it would be that many cubic units. All right, and now the important thing that I want to point out here for the disk method is that the disk method can only be used, when your area, so this shape that we started off with, I'm just going to shade this whole thing in, right? This original shape that we started off with, I think it was the function f of x equals x squared from 0 to 2. Yeah, that was it. So whenever you have that original function, the only time you can use the disk method is when this area that you remember, the whole idea is we're going to take an area, we're just going to swing it around an axis. But the only time you can use the disk method is when the area is perfectly laying next to the axis of rotation. And so in this case, the x-axis is the axis of rotation, and you can see all along here that the area that we're looking at is perfectly laying right on top of that axis of rotation. And so we can use the disk method, which is the simplest way in order to find the volume of rotation.